Okay, hello everybody. So my name is Matthew, and I'm going to be presenting with you today on my project for this semester in data science. Specifically, this semester I decided to study Morse code. It turns out that over the summer I worked on a small robotics project, and as kind of a toy example in that project for experimenting with different ways to control the robot, I got into Morse code. It was a fun exercise over the summer, and so I wanted to take an opportunity this semester and try to figure out interesting ways that it could apply in terms of data science. Now, you may be asking yourself, how does Morse code even pertain to data science? And it turns out, like, in a lot of different ways. I found out in the first sprint that, in fact, audio itself is a very bountiful source of data. Sound is all around us. It's in our language, it's in our music. It's in our natural environment. Nature makes its own sounds all the time. And a lot of our modern infrastructure and technology actually relies on either sound waves or waves more generally, whether they're, electromagnetic waves or, astronomy, radio astronomy uses waves. Like, they're everywhere. Waves and signal processing are bedrock of bedrock importance to a lot of our modern life. So it turns out that it's actually a great field for data science, and it's interesting, and it's a different type of data than a lot of these tutorials study. So it's one that I wanted to take on. With sound, just like any other data that you might be interested in analyzing, you can do feature extraction on it. You can do exploratory data analysis on it. You can do machine learning with it. You can do pattern recognition. And this is actually where I thought I would do this quickly over the summer, and it wouldn't have been that difficult. It turned out that it was a lot more difficult, and it remains quite difficult for a number of different reasons, some of which are a little bit more complicated than I want to get into in this presentation. And then the other thing I want everybody to think about is that this is actually, in a lot of ways, is actually a big data issue as well. And I think the best example of why that is, so I would point to the monitoring facilities that the FCC has in place all over the country to monitor our wireless spectrum, to make sure that radio broadcasts go on uninterrupted, that military satcoms aren't being interfered with, and so on. But also, like, when natural disasters strike, the FCC and the FEMA, the emergency response, and the Red Cross, all actually depend on signal processing in different ways to aid people in disaster and actually save lives. So in that sense, this very much is a big data issue, particularly in crises and things where the radio waves get quite polluted with all sorts of different signals, some which are very important. So I think Morse code in that sense is a particularly interesting thing to study, primarily because it's a very human protocol compared to most of the other modern protocols like 802.11, which is your Wi-Fi routers, and GSM, which is what your phones use, or LTE, which is the newer protocol that your phones use. All of those things are very much in the technology domain, and they're not understandable by humans in the same way that Morse code is. And Morse code, like I said, is very human in the sense that you could learn Morse code in a week or two and be off to the races using it, and it has this unique feature of being able to reach thousands of miles with just a few watts of radio power, which is unheard of for something that's as simple to implement as what Morse code is. But for those same exact reasons, it's not friendly to computers to decode because it lacks forward error correction and any other of the nice features that ensure data integrity. So that really ends up being the complication, and why it's difficult to study, and why I'm actually doing this as research. My study in this now has multiple different types of code and programming that I've compiled and used over the summer and over this semester. Personally, I've developed some apps in C++ that generate the Morse code. I've also got some Python code that runs a front end for the app that I developed that I was researching with before I started this. I also have a bunch of different shell scripts for file handling. I have, I'm a big user of Git. Now, of course, any other sorts of dependencies and things that are specific to my operating system and whatnot, those are all things that I depend on and use for my research, and I've gotten used to using. And now, of course, I'm also in this class I was also building in, using R, the statistical programming language into this. And so my specific problem and what I was really trying to address is that basically every off-the-shelf tool that is available and commonly taught for data science has some sort of limitation. So specifically, Jupyter Notebook is a common choice, but personally I find that it's quite antagonistic to exporting the notebooks and sharing them. Jupyter Notebooks, if you dig into them, have a lot of metadata attached to them, which makes them quite unfriendly for version control. Anytime you open that file, regardless of whether you make a change to it or not, the metadata gets updated. And so when you try to commit that to your repository, you're going to have a bunch of metadata junk that tries to commit and shows up as changes when really no changes were actually made. So I've personally grappled with things like that in the past. And I just find that a lot of those tools really are not that good for independent research where I need all this flexibility that I can't get otherwise. And I found the same thing with RStudio, which has pretty strong ties to the same people that developed the Tidyverse, and so on. And of course, on the other end of the spectrum, if you want maximum flexibility, you can just make shell scripts. But the problem with just having raw shell scripts is that they're difficult for most people to understand unless you're very familiar with doing work like that. You have really no idea what the shell scripts do, and it really falls short of telling a story with your data, which is kind of one of the core things of data science, is you're trying to tell a story, right? And you want people to be able to understand your work. And I think most people will find that's really hard to do with just raw shell scripts. And so, I think like the rest of my peers this semester, we all kind of struggled with this. And so this is what I ended up doing for my solution. And I learned about this and I built on this from last semester, but basically, I like to stick with Linux personally because it's free in the sense that I'm free to do what I want with my software. And then I also built a Git server of my own, which is actually on-premise to me. It's actually portable and goes with me everywhere I go, just like a flash drive does. And notably, it lacks all of the restrictions that Microsoft's Git platform has. Has none of those issues. I can upload any file size to it, any file type to it. I can change it and customize it as I need to. And really the same thing with my Emacs and my org mode. But I think most importantly, two other things that are really important about the tools I've chosen is that R was a good language for my research because it not only has a lot of different libraries for a lot of different functionality, like the audio processing libraries I chose, but they're also quality libraries in the sense that researchers chose these and developed these with oftentimes a lot of mathematical papers surrounding them that explains exactly how their algorithms and what their methodology was when they developed them. And I think that was really important. And then the last thing with the org mode, which extends Emacs capabilities, it's what I guess I've seen it coined a couple of different times, but they call it basically a polyglot notebook platform. So contrary to Jupyter Labs and notebooks like that, where you can run different languages but not in the same application, with org mode you can actually seamlessly run multiple different programming languages in the same file right next to each other. And so I found that really handy for my purposes, and I leveraged that a lot more this semester in my research than I had previously. So I combined different eList customizations, which is actually the language that Emacs is written in, so I can drive the behavior of Emacs on a per file basis, and also integrate bash scripts that clean up and commit my work automatically, all into the same file. So I thought that was a really powerful tool for this semester's research, and I tried to really build on that. So I wanted to show you guys briefly just some of the work I ended up doing, kind of hit the highlights of my research. So first in the EDA section of my work, the first thing I had to do with the data set that I had selected was I had to check all the different files for corruption. It was something that the author who wrote the data set mentioned, that they'd had some issues with uploading the files and that there was some corruption. So I had to basically go through and check and see, how corrupted were the files potentially. So one of the key metrics I had for that was the sample rate versus the length of each file. So basically I expected this to be linear. If they were 8,000 samples per second, which is pretty standard for telephony signals, then I would expect each file, depending on its duration, to have this same pattern. So I basically ended up graphing that once I had all the files loaded, and realized that yes, that was a linear pattern. So at least there weren't large sections of each file, or more samples than what each file should have in it. And that was really useful right off the bat. That was like one of the first things I did with all these files, and it was good information. The next thing I looked at was the actual coding rate, which colloquially can be kind of thought of as like a words per minute. It's sort of like if you're learning to type. And from what my research indicates, most experienced operators are able to type at about 28 words per minute. Then there's sort of an upper end around 50 or so, and a lower end somewhere around maybe 10 words per minute if you're learning. So I went ahead and derived that with the data I had, given that each file had the same number of characters in it. And I kind of realized this nice bimodal distribution. So basically there's kind of two camps in the data. There's one camp in the low to mid 20 word per minute range, and then there's another camp up here somewhere around the mid high 30s. And there's also a little bit of a hump down here, but you can see that a lot of the data kind of trends towards the median, which is good. And then there's maybe two different camps here, kind of to indicate what you might see in the real world, where you've got some amateurs, and then you've got some more experienced individuals up here that are coding at a slightly faster rate. So if I was trying to develop some sort of software using this data set, I think it'd probably be a pretty good candidate, because most of the data is what I think I would probably expect to find in real life, even though this is actually synthetic data. The next thing I learned from a guest speaker that we had come to present to us was that a lot of times student researchers are bad at testing for edge cases when they're investigating things. So I tried to do that as well. So I looked into what were potentially the cleanest and the most noisiest files in the data set. And the way I ended up doing that, we'll go over to the main file I made here, my main research file. The key indicator I found for that was the root mean square amplitude in each audio file. And I found that the root mean square amplitudes that were very high tended to indicate a clean file, and then the ones that were very low, particularly outside the interquartile range, were very noisy. Hopefully you guys can see that here in this file. And so basically I ran with the tidyverse, and I sorted out for the files that did have a prediction, because that was the ones I was interested in for training data, that were the cleanest and the noisiest respectively. And then I used them consequently for generating a lot of my graphics and whatnot later on. Whoops. And okay, so here you can see, here I've got an example of a very clean file, the waveform of a clean file, which is, this is the amplitude and the time domain. And you can see these files are very readable, and I've marked up here, this is an E8, G8. This file is very easily visually readable. This corresponds to exactly how the existing decoding algorithms that are in radio hardware actually work. They literally just look for the amplitude when it spikes and measure the how long in the time domain it spiked for, and it would reason that that's a dot, and then there's a space, and then there's 3 dashes, 2 dots, and etc. And it just decodes based on that, following a tree structure. Now, contrast, here is what one of those noisy files that I just showed you earlier looks like. So you can see in this file here, visually, there's nothing to see. The background noise is high enough that you can no longer discern what the signal actually is. So, what to be done about that? So also using these audio processing libraries that I found and installed on my system. This one here is Tuner. I opened up this dirty audio file and applied the spectrogram, which actually transforms the wave and allows you to see basically the same signal in 3 dimensions. So now we have the time dimension, the frequency dimension, which are both of your domains, I guess. And then you have this color here, which represents your amplitude. So now you can see on that same file, I haven't adjusted it or changed it in any other way other than just applying the transform to it. You can see now that you can easily tell, oh, this is a dit, this is a dash, dit, right? And you can decode this. So this ends up being where most of the current research is being done in this field, is by analyzing these visually and trying to decode them this way. But I wanted to take a little bit of a different way and see if I couldn't transform these files back to what could be used by the more traditional decoding methods. So what I did was I developed a filter that basically comes through here and discerns where the where the signal actually is in terms of its frequency. So you can see these here are approximately 600 hertz, which is a typical Morse code signal frequency. It identifies that, and then it automatically applies a filter to it. So this graphic here, you can see what the same audio signal looks like after the filter has been applied, and now you can actually read it in the regular waveform as E, Z, and R. And that's pretty much what my research came up with. So one of the things that I was really proud of is that I was smart, and any of the functions that I had to develop specifically to tailor the audio libraries and the files that I had to download and use with my research, any of those customizations I actually built into this functions.r file. I actually tangle it to this file from another org mode file that has all my notes on and my reasoning on why I developed what I did. But that script now is here in this very generic .r file, so I can reuse this later and reuse my same research if I ever develop this into an actual application or something like that. I already have the starting point already here to do that with. That's another unique feature of Emacs that you really don't get in Jupyter or anything else like that. I think that was important. I didn't get as far as developing an actual decoding algorithm, unfortunately. Really, I think I really just ran out of time, and the problem again was more difficult than I anticipated it being. But I did think that the Fourier transformed versions of the file were pretty cool, and I think there's a lot of potential there. I can see why the other researchers are pursuing that as a means of decoding these things, and I think it's definitely worth pursuing that more, and that's what I'm planning on doing later on. And I also found that my research, of course, takes a little bit longer time than what it does maybe using some of the off-the-shelf, more polished solutions, but I don't think I'd have it any other way. I like having full control over all of my research in that way. I don't want to be limited. So anyway, guys, that's what I found. I went a little over 15 minutes by about 2.5 minutes, but I got close enough. So finally, here's my reference page, all my references I use in the project, which can also be viewed in my actual abstract. And if anybody else ever wants to watch this recorded presentation again, they're free to do so by navigating to this link here. So I hope you all enjoyed, and I look forward to seeing what everybody else came up with. Thank you. Bye.